All right. We have started one of the most important steps in any analysis, and that is segmentation. So segmentation really goes to images and then looks for a discrete number of phases of interest. And those phases, if you're looking through the lens of X-ray tomography, then we know that X-ray tomography really displays some function of density on the image. So the phase can be described as materials or physical materials that have certain density. If two materials have density that is very similar, we will not see them on an X-ray image. So they might be physical phases that are different. It could be water and water with a polymer. Same thing as far as X-ray is concerned, because the density doesn't change enough to actually register. I need to have some contrast agent for that to be the case. And that's common in any kind of imaging, right? Your images see what they see depending on the equipment, and that's what you're seeing as a constant phase within your image if your imaging is done well. Other than that, you need a contrast agent, right? Okay, so when we have air and another fluid, typically we're good, so we can see air, which is nothing, versus almost nothing versus something that we can typically see. So in this particular image, and I have just gotten, this is from Dorothy Wildenschild in Oregon State University, who's been imaging things with X-ray for a while. She's in environmental sciences, so her models are typically modeling soil, so a lot of work is done in sphere packs, and also you can control sphere packs quite a bit. So, and she is actually visiting in April, so we will have a lecture, or I will make her give a lecture, because I think she'll be here on a Friday or something like that in April. So in any event, you will see much more images that are coming from her lab. In the meantime, we will look at this one example, and a number of examples are actually from her here. So this is basically my water, this is air, this is beads, and now this is an image. This is quite a large image from X-ray. I would like a labeled image, which I refer to as segmented image, that identifies all of those phases, and there's air surrounding it, but it could be some surrounding something like aluminum or plastic or whatever is cylinder that is containing the beads. So this process of separating voxels or pixels into some distinct groups based on whatever your imaging can actually recognize is called segmentation. And you want to first count everybody up and see how many of each do you have. And then there are various expressions for that. So in terms of fluids, we will speak in terms of saturation. So I would like to know what is the saturation of air or water in this particular case. A lot of constitutive relationships depend on SW, which is wetting phase saturation. And that's what you want to evaluate from an image in order to possibly provide another constitutive relationship or compare with the one that you're using theoretically. Right? So how do we actually do this segmentation? So everything else then depends on it. If you don't evaluate your porosity or saturation correctly, well, everything else can go down the drain, right? So we need to actually trust these numbers. So segmentation typically, or any kind of image information that we use, typically uses image values and gradient of an image. And I already went over that last time, so I will not labor more. And we were also cleaning the images up or filtering the images using these same things. So typically, the only thing you really have is image values and some sort of differences or spatial differences, normalized spatial differences of those values. And any other kind of fancy filters ultimately come up with some combination of image values, possibly normalized in space in certain direction, That's all the filters actually are. So basic idea is that if I have an image that is good enough and I can see all of the phases that I have interest in, then once I do the histogram and statistics on this image, these different phases will show up as distinct peaks in this histogram. Okay? Now this does acquire, so sometimes you can actually have or distinguish things really well. Sometimes on a histogram itself, you don't necessarily see a peak because there's very little of it. And that can definitely, when there's very little of something in your image, that's going to affect your ability to identify it for sure. So for instance, here we see that we don't have, in this particular image, I don't think it's one of the previous ones because this is oil, glass, and water. We have, so, but what this shows is that if I had oil and glass would actually share, and water was doped with something. So it was more attenuated. It had intensity base separated from oil. Otherwise, I would expect them to have very similar density. So X-ray should see them as similar. And here, if I have air phase, it typically is very well distinguished from any other solid phase or liquid phase. So good separation on histogram basically also shows me that I have pretty good image. So this is an example image from here. Now, if I have a bad image, and this is my quintessential example of a bad image, this is my own frustration from my PhD when images were not as good, okay? Then all of the noises, so for instance, here we have ring artifacts and they're messing with my identification. My eyes see relatively smooth surfaces. And I actually know for a fact that polyethylene should be smooth. Those grains are pretty smooth. They're a piece of plastic. When you even look at them under SEM, they have actually very nice smooth surfaces compared to most of the mineral surfaces of real sand. So they shouldn't be this rugged the way this segmentation gives me. So this is a pretty poor result. And this is what just doing a simple cutoff, as suggested here, right? Go to the value of intensity. If it's below a threshold, set it to one phase, and if it's above a threshold, set it to another. It's as simple as that. It's really fast. Okay? If I asked you to program in your favorite programming environment, you would sit down and write it down in 15 minutes and debug in another 15. Okay? Now, that's really fast, but this image, and I already see that this is a pretty bad image. This is the evidence of it being bad. Look at the peaks. I barely have peaks. They almost overlap. Even though I have a decent portion, pretty much close to a half of this image is empty, or in this case, oil phase. This is oil phase, by the way. And the other one is polyethylene. It's about 50% porous. So about 50%, so I have decent amount of both. It's just that they overlap so much because of noise. I have inside polyethylene these dark pixels that shouldn't be dark. They're there because of noise. Right? So that then results in this overlap. So if you have a histogram that looks like this, no threshold will work. A lot of times in segmentation, because thresholding is so easy, a lot of people spend a whole lot of time finding a magic, what I call a magic threshold, in order to segment the image. No, this is not filtered correctly. No magic threshold will help. Okay? So you can maybe spend time filtering the image a little better, or using an advanced segmentation method, which technically has some of these filters built in. Right? So in that sense, simple thresholding most often doesn't work well unless you have a very clean image. Okay? But again, it's very easy to conceptualize. So if you have high quality images, yes, these are pretty good. Okay? Though we will actually use one of them as practice, so you will decide for yourself. So this finding the magic threshold, there's a lot of methods that are attempting to do that and basically try to separate these peaks the best and so forth. One of the most common is so-called Otto's method, selection of these thresholds from gray level histograms, and it's actually implemented in ImageJ, so we will give it a try. But no matter what, quality image is a prerequisite. Now, if you actually ask users, there's certain subjectivity to this. Unless you know, and you don't know, otherwise you wouldn't be analyzing the image, where all of the phases are, you don't know what threshold works the best. Right? So it's a bit of a catch-22 question, right? So you can evaluate methods on those in those cases where you know really well, but after that you have to trust the choice of threshold. So there's certain uncertainty with the whatever threshold chosen. Right. Now, if you have images, sometimes you have a high quality. This is a photograph. Okay. You have a high, this is a fluid in a capillary. If I asked you, how would you rate this image? It's really sharp, right? The problem with this image is that unfortunately, because of the curved surfaces that look different. So here, solid is a solid, fine, but then there is certain reflection in curved surfaces here. And because of that reflection, you're getting these different shades of gray within what should be an oil phase. So if I want to distinguish, I'm interested in finding where is the oil, where is the water. There's water, oil, and glass here. Segmenting based on the grayscale value is not going to work here. This is what you get. There's some gray values here that are darker and not so dark elsewhere, and this is not physically meaningful. Okay. So it depends on the method of the imaging. Is the imaging that you're doing actually clearly distinguishing different physical phases? Right? Here, I guess this one is outlining boundaries, but because of the reflection, it doesn't do boundaries sharply. So processing this to actually find the boundaries would require some tracing and a lot of input from the user. This would be similar to if you had foam bubbles under a microscope. If you're interested in finding foam bubbles, you would see kind of circles, but you wouldn't clearly see the difference in the phase, meaning gas versus fluid around it, or if it's emulsion, two different fluids. Yes? So again, image has to clearly, the grayscale values, all you have is really to work with is grayscale values. And those should be clearly associated with whatever it is that you want to identify. Otherwise, segmentation per se is not necessarily the method to use. So this is just a warning. So there is a very good review paper on segmentation for porous materials. Okay. But technically, what you have is this some sort of global thresholding. I globally apply a threshold, and then for all of the pixels or voxels in the image, I go one way or the other. There's so-called statistical, where I'm trying to cluster the phases and try to statistically make the phases as separate as possible. And then some sort of local adaptiveness to the image. This local adaptiveness will typically not look at just the value itself, or it will maybe start from certain thresholding values and then adapt from there. Often it's looked at as looking at the gradients of the image and making local decisions based on the gradients, as well as what would the probability be for my pixel to be of this or that value depending on the neighbors. There is also region growing, so I start from a region and I try to kind of grow and compete. And these, we will see, they're often called active contours. They will grow at certain speed and possibly slow down or speed up depending on what the gradient is. The idea being is that if I'm in the same phase, my gray values are not changing as much, so I can move faster. And if I come to the large gradient, I should move slower and gauge where so that's physically what the idea of this region growing, level set, active contours, watershed, those are all the different names used for this group of algorithms. And then manual segmentation, which I do not like to talk about. I'm applied mathematician by training. I do not like doing things manually, just by trade or by training or whatever. So I like algorithms, so I like automating things. But trained users work well in 2D. It's hard to avoid bias, so you need trained user that has seen things a lot. And for big fat no. It's a no-no for 3D volumetric images simply because of their size. There's no way to process enough information in 3D. This is how segmentation, now it's aided, but definitely was in medical imaging. Okay? Even if it's in 3D, but in medical imaging, if I'm doing slices through the brain, I'm going to have 1, 2, 3, 4, 5, 10 slices across an entire skull, right? Or brain. 10 slices I can do. If images are 1,000 by 1,000 by 1,000, you cannot do that. So in those images, you will often have, if people are searching for a tumor, right? Tumor is a different phase. It does have different densities, so it's going to show up on a CT. So you're looking for an object in there, right, and segmenting that tumor. And a person can manually trace it because geometry of the brain is not all that complicated. In porous media, it's hard to resort to that. Where it's resorted to is in analysis of thin sections. They're so-called point counted, but all it's done is that there's a program puts a raster of points, a grid of points, and then the trained user decides for all of those points, did it fall into a pore, which is epoxy, so it's often blue. Right? Is it pore, is it microporous, or is it grain? And maybe different types of grain depending on the type of image. Right? That's called point counting. It's labor intensive. It's done in geology a lot. And it's somewhat more complex to write an algorithm for. So you do need to train this algorithms, you do need manual segmentation, but overall manual segmentation you don't want to do for volumetric images, period. All right, some user interference, no matter what the method is required. Okay? If it's not required, then maybe we have the latest generation of machine learning or deep learning for segmentation, but that they were trained too, right? They were trained on something, right? They were trained on some labeled images. Okay? So they didn't start from nothing. It's just that then they decide on those thresholds using the knowledge of the training done before. Okay? So it's still user interference, however you turn around. Okay? So good paper. This is a paper from 2009. It's not going to have machine learning methods. But now there's a whole number of them showing up. All right. There's also statistical region merging. I'm going to maybe now move on to, let's see. I'd like to try something out. And then I'm going to get back to let's do an exercise, okay? And then we're going to get back to more. So let's now try out some of the simplest explanations. And I'm going to quickly share data with you, which I failed to do before class. So we're going to come back to theory after we actually get to do something. So open up your Fiji or ImageJ. Okay, this is all we need. So we'll go to data. So this is going to be all of the segmentation exercises we're going to do. Share. So when my links don't work, that's because I didn't click this to change the default value to people with the link, by the way. I don't know if you ever share stuff using UTBox. Invited people only means that you share that using UTBox, and those people have a UTBox account that is recognized, which most of the time is not the case. So often when I'm quickly, either I don't do this correctly, and then I send the link, and then I get all of these emails. Where's the data? Why can't we see the data? Canvas. In Texas. It's funny, it doesn't recognize that I'm. There we go. So follow the link and go to data beads folder. In that folder, download the entire folder. So we need to import raw for this data. Segmentation. And now this is 695 by 695 by 200. Data is 16-bit unsigned. What other information do I need? Indian part. So, yes, raw. This one, beads dry, 16-bit, NX and Y and Z raw in data beads. And it's big endian. It's not little endian. If you do little endian, you're gonna do a soup out of that data. You can make that mistake, see what happens. The result might be interesting. There we go. So beads underscore dry dot 16-bit dot NX695. Again, do the mistakes, see how it looks like. Okay. So you can see these are just glass beads, just glass beads. And you will see first some of those glass beads have defects inside because, well, depends how much money you spend on your glass beads, really. It really does. Not all of them are super spherical. They should be, even when they tell you they're gonna be in a certain size range with certain probability. So they're gonna say 90% of your beads are in size range from 0.8 to 1.2 millimeters, and you're shooting for 1, right? So just be aware of that. And how much money you're willing to spend on them, they're gonna be better at being all the same size and smoothness. These are certain motion effects that are done during, so maybe sometimes beads are moving. So there's something happen here. So image is never perfect, just work with that. This is relatively clean image. But all of these little defects will affect my segmentation ultimately. And I do have a little bit of rings, but not too much. This is just a holder. So this is just, yes? Okay, excellent. So we have read the, so this is how successful. These are actually defects on the beads. That's my understanding from discussing with Dorothy sometime. This is data from Dorothy Wildenschild as well. So this is simply the beads. Now, if you want to perfectly model it as bead, well, it's not a perfect bead, right? If you want to remove that defect, this is a real one, okay? This is not real. This is a ring artifact. Okay? So some of these things are real and they're not perfect, but they're realistic. That's what it is. You imaged what is. Okay? In this case of a ring artifact, you did not image what is. There's just a problem on the detector. Okay? And so there are certain motions, like things are supposed to be static for the 10 minutes or so that it takes to scan, and if they're not static, then you get these motion issues. Sometimes beads actually move. I mean, if they're not in a stable position, you have to put it into a container, right? All right. Okay, great. So this is the data. And first things first, so we have things outside here that we don't like, or you can feel free to do segmentation on this, but if you want to just focus on just where the beads are in the container, then you need to fit an oval and do that clear outside exercise, right? So let's try to clear. And also while doing so, let's learn to do that macro record so that we know what you're doing. And my suggestion is to do something close to this. When you're fitting an oval, the center should be about 74, 84. Well, Z doesn't matter. And width and height should be 538. That's what kind of worked well. So when I'm picking an oval, okay, so I'm now at 74.84, so now I just need to fit these. Almost there. You know what? I'm gonna go with 500. Ah! Sorry for the sound effects. I'm gonna be a little more conservative. I'm gonna get height and width 537. And then now what you could also, so obviously this also shows you, this is why I wanted to record. This shows you that this is the command that is executed as you're doing this. So you could just create a macro that has this information, 74, 84, 538, 538, and execute it. You can run a macro. Create. You click on this image and then run. Okay? And now what's executed is 538. Yes? Let me prove it to you that that's what's executed. I'm just going to kill an 8. That should be shocking enough that we see it, right? Run. Oops. Yes. Let's also assess something. So this should be working as you're moving through. So as I'm moving through Z, look how the position slightly changes. So what's the Z direction of the imaging? Now this is not a large shift. This resolution of this was 17 microns, I think. 17 times 200 is what? 17 times 200, 3400, 3.4 millimeters. So we're talking about cylinder this big. Okay? So yeah, it was tilted by, you know, very small angle. But that small angle you're going to see, huh? Yes. You can, I guess, write an algorithm for doing that. So you can figure out, by placing this, you can figure out what the shift is here and what the shift is here. See? And basically, there's a translation. What this. So what I would do is I would go and fit a circle of the same radius to the bottom and to the top. Same radius, that it fits the cylinder. This actual physical cylinder. It's going to be slightly shifted at the bottom compared to the top. This X and Y here will be different. Okay? And then you can move. Here you have enough padding on the side. Your region of interest is inside enough that you can then move the bottom images, you can shift them, but you can progressively, you have to progressively change, you have to graduate through all of the slices. But you can do that calculation. That has to be done constantly for these type of things. Because the way you record or assemble is not gonna. And often when you put things in, it happens downstairs in the medical city a lot. Things are hanging. There was so slightly shifted. We're talking about a few millimeters over this, but you see it in images. It's annoying as hell in images, but it's what it is. And if you are then processing this data, that can introduce, of course, the error in calculation of porosity and everything else. What I like also doing with understanding that there's shift, just maybe make this a little more conservative and move it to the middle, so that you're away from pulling away from the boundary, so you're more inside is not that bad in my opinion. Whoa, and now I killed it. Compared to getting into this boundary here and counting that as some type of solid that isn't there. So I just kind of shrink my oval a little bit. So if you're bothered by that, by all means, let's try to do this. Run. And question is, are we always on the inside, right? I think this is pretty good. For this exercise, I'm going to keep, you can play with this to make it to your liking. All right. And then clear the outside. Clear. All right. And for some reason, my background is set to this beautiful shade of gray, which is the default value somewhere in image J that I'm not going to now track down. But we can actually see, oh, so value is 35113, which seems to be right in between this and that, which can be problematic in various ways, but I'm going to leave it be now. What is your default?
65,000.
Again, it's probably options. Somewhere in here is a background. Is it appearance? I'm going to test appearance. No. So I'm not going to spend time looking for it. It's somewhere in there. Okay? It's an option. And that option, I don't know why my version has a default. I don't recall changing it, but that doesn't mean anything. It might have been changed. Okay. Okay, excellent. So now if you do, regardless for the purpose of this, if you now do a histogram, it's going to take only, yes. However, if I export this as an image and now send it to my favorite other software, that other software will regard this as an image, and this is going to have values of 35,000 or whatever this thing said. So what you can do math on it and take this constant value and just set everything to a 0 or a minus whatever, like some value that you will know that is way away from the spectrum that you're interested in. So these things can be, but ImageJ will ignore this. So as long as we stay within ImageJ, all right. So this is a two well-separated peaks. I do have sort of a code that they don't sharply go down to 0, right? They're not, but wherever I put the threshold, this is not a lot of pixels, okay? Even if I do log scale, you can see that on log scale they show up, but only on log scale. So this is not a lot of pixels. So whatever error I have in choosing a threshold, whether I choose it here or here or here or here, that will definitely have some effect in the porosity I calculate, but it's not going to be large when I divide by the total number of voxels. that's one way. Yes, you will always be making an error. Is that error sizable? And if it's not sizable to a certain level, move on. Okay? There's always an error. Welcome to the world. Right? So it's, and then fix it if you need to fix it later. Maybe you will do certain analysis where this error will become a problem, and then you fix it. So anyway. Okay. So different thresholding selections here. So you can pick your own threshold. But here there is a just threshold. Okay. And it can show you, so here you can see that the just threshold does take that boundary. So I would actually have to go and find where my default value of the outside is, because it's taken into account. This is default. Otsu is that famous method. Works better in my case. Look at this little bit of business going on there right outside of this. So the fact that your default is black or white will save you here, because you will not get this behavior that I do. You somehow switched to RGB. Are you trying to do, this now is red, green, blue because it has obvious red. So did you at some point try to threshold this? Because that would be a problem. I'll take a look. So that's the thing with clicking is nice, but also if you click on something, yeah, threshold is a histogram. It's an image. As far as image J is concerned, it's an image. Yes. So small things, I'm gonna spend one moment on it. So small things do matter. So here, the choice of my background is annoying. Now picked up some of, just a little bit of outside of that background, pretty much where my mismatch of my, whatever that I, mismatch between it and that solid boundary. It has identified that piece of the outside as a beat in this case. I want this red face to be a beat. And in the process, I picked up some of this. This is something that is always there. So you have to work with that. Now, if I'm just evaluating porosity, and my only objective is to find what porosity is, not a big deal. I'm not going to write home to my mom, oh my goodness. My mom doesn't care. But she did. I'm not going to write a letter saying, talk about it as fact. Version of writing a letter. So, right? But if I have to somehow work with that boundary, find the surface area of that boundary, this is going to bother. It's going to start bothering me. If I'm trying to send this to meshing for finite elements, called good luck. You're not going to survive. Any kind of small features, So, question is also what are you going to do next? So sometimes you're happy with the result for now, and maybe fix it later for some other purpose. Just prepare that. Alright. So, while I'm going to actually go find where my background color is and go fix things, I will task you to adjust the threshold to something you're happy. So when I was actually creating these files, I had a white background and I had no issues. Okay. And kind of walk through the sizes, see how happy you are with the choice of the threshold. So I'm just gonna comment on that slightly. So you will see here near where you have problems in the image. So here there are some shifts, but this is a decent result. You might need to read in your original. Okay. So here you can see how some of these, but again, beads had some of these beads have dark inside, which is a defect of the bead. It's not a defect of the imaging. Okay. So just evaluate visually how happy you are. So some of these speckles that show up inside of a bead are physically there. Some of them are maybe a problem of the imaging. For now, we will just assume that there's not that many of them. And then you can convert this image to binary data by hitting apply. When you're happy with your threshold and you have played with it enough. So this is where ImageJ kind of, you hit apply, which in my case is not gonna be. So you can see now how the problem, this problem with the boundary is showing up. I'm gonna leave it here because it actually teaches something. So you can see some of these issues that show up near the boundary. So you can choose whether the background will be black or white. That was actually before I hit apply. So it might, in my case, I chose dark background, which it'll be better probably to have it opposite of whatever pore space is because I'm interested in the pore space. But it depends on application again. Here, I had settings that were, so which one in this, whoa, so now I'm thresholding this and now it's saying, well, nothing to threshold, everything is black and white, right? The moment I click. Let me pull up the original again. So just to point out, image adjust threshold. Okay. So which one of these is going to show as red? It kind of depends. So here it shows those values that are not so dark to be red. And it shows you here what's choosing. It's a choice. Right? What's on your computer? What's the default? Right? So then this is red. Right? Now, why did it flip this? It's again, it's a dark background, maybe. Ha, there we go. See? So you flip that choice. See how it flips? So you can play with that. I didn't fit the oval, but actually I think I kind of like this. Without fitting the oval, I can fit the oval later. because this is solid and this is solid physically, and I'm interested in pore spaces, right? So I can now apply the oval. So the order of these operations kind of depend on the image you have. That's why I'm kind of staying a little bit around here and discussing, because these things, these choices do ultimately matter. Yes, you have a choice, but the choice you make identifies background in a certain way and the rest in a certain way. Okay, so now I want you, so once you have binary data, this is binary data. So what image J, and that's again a matter of choice, works is with binary data. It shows them in as black, 0, white, 255. I'm used to working with 0 and 1 for things, and a lot of segmented images come as 0 and 1. 0 and 1, though, when you're actually showing here, would show it all as black. So don't be scared of that sometimes. It's just you need to adjust brightness to actually show the differences between 0 and 1. Okay. You can always invert image. So there is invert. Boom. Okay. So now this is 255 and 0. Again, it's arbitrary, but it is ultimately important, and you need to know. And the way you find out is by literally moving your mouse around and seeing which values show up, so you know which one is which one. If you wanted to now, do you remember how to look at the slices in all of the directions? Orthogonal views. Here we go. So you can see that they're all kind of the same in all directions, which is good. That's so nothing is squished. All of the Z spacing is the same as X and Y. Whoops. And my third one, there's no space when I'm projecting for all of them. So you can inspect your image just like you would. So orthogonal views. So now I want to know what the porosity is. How are we going to find out? Histogram. Now, if I do this histogram on my image, okay, I don't have that oval. Right? So remember that that can be a problem. So I'm now going to move. That can be a problem because all histogram does, it counts black and white. Okay? If I put an oval, okay, if I put an oval around and ignore the outside, so now I'm just gonna, or for the heck of it, I'm just gonna do rectangular. Whoops, I need to kill my orthogonal views. Or maybe make an oval, right? There we go. Run and clear outside. Still setting this value. Okay. So now if I do a histogram, oh, there's two. I'm gonna go through analyze histogram. Yes. There's a 0 count, which is my black values. And my white count, which is these. So this is the pore space in my image. It has ignored this value here. Right? My histogram did. So now how will I find porosity? Well, I can calculate what the volume of the cylinder is. I drew it, so I know what the cylinder is. Right? I can sum up black and white values because these are ignored. Right? So there's multiple ways, but what is also depends on the choices, how you go through these procedures, what is how is outside labeled, is it counted in your histogram, and so be sensitive to that. Get it? Yeah. In this case, the way I did it, yes, you can. However, if this background was white or black and counted in the histogram, then no. Okay. This background for me is 140. And it doesn't appear to show in the histogram. I can check that actually right there. You're going to get a peak if it shows up. But that's because clear outside is correctly not including this 140 right there. So you have to be careful with that. And again, we can figure out. All right, so now I will go back to a little bit of just wrap up of. Now you got the idea what global thresholding does. And it's not the only choice, and we will go through some better choices. So one statistical value is that statistical method that I use to work with is probabilistic. So basically, it takes this pretty bad image and it calculates, it starts from a starting point. So based on the histogram, this is the histogram. So you can see that it's barely seeing two phases because of the noise, even though my eyes see it pretty badly, pretty well. So it says, okay, this one is a safe histogram. So I'm going to say, okay, everything below this histogram, this value, is surely my white phase, which is here, my darker phase, which is here, this. And above that is surely the other phase. I'm not certain about these in between values. Okay? So you have the basis, even if the histogram is not bad, this thresholding gives you a starting point. And then for everybody in between, which everybody in between is here red and white, actually in this image. Those are in between values, then you let the method choose. And this method is trying to also separate these two phases, but it's trying to do so relatively smoothly in terms of the boundary between. So you can see everybody that is yellow here ended up being white in the final. And everybody that's red here ended up being black, and that's pretty good. So because a student before me figured out this segmentation method, I was able to actually use these images and get a PhD. Or rather, otherwise, my PhD would be in segmentation, but it wasn't. Okay. So basically, I was able to work with this. I actually then adjusted as part of my PhD this method to work with multiple phases. That was one step because I was looking at oil and water separation in Berea sandstone. Okay. Now, how do we evaluate segmentation? So we can have a number of methods. And question is to yourself is, how do you know which one works well? From the theoretical standpoint, you could give it a test. So you could take an image, throw in some noise. So you have a ground truth. That was your starting image, black and white. You throw in some noise, and then you let the method choose. Okay? And then you evaluate how well did it do. So that's a modeling. I call that a modeling way to evaluate. And it's fine, except that this is a test with white noise. So there was an original image with white noise. And then simple thresholding will fail whenever you have this randomized white noise. Simple thresholding fails badly. This is one of the algorithms that was used before in the same group, and then indicator kriging did well in this test. and this is how it was chosen as better than the previous contenders. This is good. One part of the problem that you do have to be aware of with this is, does this noise that is here in the image, does it really emulate the noise that is there because of the imaging or reconstruction? And the salt and pepper stuff that you can throw into your image is not always realistic type of noise. Yeah. So that's just something to it's statistical noise rather than all of the nonlinear physical reasons why we have noisy images. So that's something to be. So no segmentation algorithm will deal well with ring artifacts, for instance, unless it knows, oh, there's a ring artifact that's precisely there where I can remove it. Okay. Now, I mentioned Dorothy Wildenschild today a lot because I'm using her data for this exercise. And she said, okay, well, is there an experimental way for me to do this? And she threw a lot of money on very expensive beads. So for which she could say, okay, these are spherical, really, really nicely spherical, right? Even when I image them with X-ray. And those are the ones right here. And then she knows what those are. Those are spheres. So your segmentation should give you back a sphere or something pretty close to it. Second part is that she imaged the whole bunch of capillary tubes with interfaces sitting in them that you can evaluate in all kinds of ways whether the interface curvature of the interface is matching the capillary pressure and contact angle that you have, right? So it's an experiment. You know what you're imaging from the outside, and if it's equilibrated, you can kind of evaluate them. So there's actually an entire paper. So basically, these are capillary tubes, different with of different diameter, and this is the image. And based on the capillary pressure that was in the system, she figured out whether what is the error of the segmentation method she was inclined to use. And what she calls a precision beatback. And there's actually a paper in 2010 on that topic. Okay? So there's different ways to evaluate. Software is constantly evolving. Most of I'm not going to go through the list. Most of the software, even if it's just visualization, the way visualization is done in 3D by any kind of surfaces, they're actually simply thresholded surfaces. Okay, so typically you're looking at the surface, and when somebody is plotting pressure isocontour, you're looking at the surface for pressure below a value and above a value. The moment you give it this value, that's thresholding the pressure at that value and just visualizing surface in between them. Okay, so we're going to get to visualizing surfaces as the next thing, but this simple thresholding or isocontouring or whatever is basically a similar. It's built into most of the visualization. Right? So software is there now. Different. We're going to focus on what's found in image J for this purposes of this. There's MATLAB is pretty good and has very good image processing routines. The problem with MATLAB is that doesn't always scale with large images. So X-ray imaging is not all that popular unless it's CT data, not micro CT, because CT images are typically smaller. Larger images, micro CT, it has trouble dealing with it. So one thing that even in this world of segmented images, even if I've done some filtering on the image before segmentation, we didn't actually touch the image, we didn't filter it, right? One could play with the image that we work with and filter it before segmentation. We didn't do that. You will still have to filter even your segmented result. This is a new image. Okay? There is, no matter what, I pointed out that there will be misidentification in that image. Sometimes it's physical. Okay? Sometimes it's not physical. So those bead defects inside of a bead, they're physical. They're there. You might, for your modeling purposes, want to remove them. And if you want to remove them, you need to be able to find and filter them from your segmented image. So your segmented image is an image. It's a simplified image. It's 0 and 255 in this case. Right? You still might want to process and filter that image. One thing that is common is that even if those small defects inside are physical and they're actually there, you might want to remove them because they're going to cause you a lot of grief in any simulation that comes later. Small features make unstable simulations. Okay? But if they're small and volumetrically are not a lot of the image, and if you're concerned about the permeability, small features, unless they're really sitting in the middle of the pore space, will not really affect your permeability calculation all that. Right? Permeability really overall is very sensitive to what's in the middle of the pore space, right? And it's the larger features that kind of dominate. The largest feature kind of in your image determines what the overall permeability will look like to an extent. So removing small features will not affect permeability all that much. So you can safely remove. However, if we're looking into surface reactions, small features tend to be near surfaces. That's where you have a lot of errors, right? A lot of noise. That can really disproportionately affect your simulation or the results from it, interpretation of the results. So you have to be a little bit careful. So one thing that also is gonna be there, if I have a thin feature in the image or connection between two things that is relatively thin, that connection might be broken simply because of a combination of the resolution and segmentation. Okay? So suddenly you're gonna see two pieces instead of one. So some misidentification has to be there no matter what. Or because of some noise, you might have a small floating object in your pore space, except that that object is not physical, it's a noise, right? So you might want to remove that from your simulation because it's going to affect the solid phases, affect the flow, right? And how the velocity profile looks like, so you might want to remove those. So some thinking is, some care has to be exercised, but typically small noise can be removed. You're gonna have a smoother ride as far as simulation goes, right? And you should just make sure that whatever you're removing, so the difference between your filtered image and your original is not huge, okay? All right. So the simplest case would be removing small objects below a certain size. So you need to figure out. You can also, if you see a lot of speckles, you could just do despeckle. Those are the filters, like median filters that we already worked with. The median filter will probably do very similar as despeckle because it's going to evaluate in a 0 to 55 image. If you have only two values, and the way median filter works is orders the values, it takes the median, and that puts that in the middle. So if you had a majority of zeros, it will replace them. We're gonna do erosion and dilation later. Those are kind of dangerous because they can change your image a lot, and we're gonna look at that. All right, so that's gonna be a separate topic. So we start with the tomographic image, which is sort of a bunch of numbers. They have their intensities, and they're stored in your memory in a specific order. And then you would like to identify who is who, and you would like to do so in a manner that ignores noise. Now you can first do a whole lot of filtering on this image in order to get here by simple segmentation, or you can have good segmentation method that will deal with things statistically or probabilistically, and that you will still get the similar result. Okay? And we're going to practice. So ultimately, you do want quality segmentation because everything else depends on it. So you do have to evaluate. You also have to evaluate your result, like how many small features, depending on what you want to do later. You will then evaluate whether your image is good enough for that purpose. One thing that I'd like to comment, especially if this kind of looks randomized in terms of noise, if I just evaluated porosity as a number, these two might even look the same porosity. So for the porosity purpose, a volumetric average will kind of deal rather well with this kind of noise, speckled noise. The problem is, if I wanted to do simulation on this, okay, I can't do. And we ultimately are not happy just by evaluating porosity. We want to do more. Okay. All right. I'm going to continue the lecture later. So I see you on Monday. And I should